So make sure you got your assignment 7 and whatever else I have handed back. We'll do this, start a new one here. So is that 124? Final exam review, part 1. I guess part 1 of 2, but we'll figure that out if you're on Moodle. Okay. So, like I said, I want to go through just practice test 1. If you've been on Moodle, you probably saw that there's 3 practice tests with solutions posted. One thing that I do want to mention is that those are just kind of broad strokes, right? So if you come across a question that you're like, oh, I don't remember talking about this, or I don't remember Emily emphasizing any of this, right? That's totally possible. You can just send me a picture of it and say, hey, do I need to know this for the final? And I'll just send you a yes or no answer, right? So I don't want you to kind of get wrapped up in some of these things because they're probably not important, right? Everything that's on the final, you will have seen, we will have talked about it, we will have emphasized it. And so I don't mind having those extra questions on there because it kind of makes you practice more. But as we go through this practice final, I'll point out some of the things that are less important and more important. Okay. And I said I would pick the best one, but like I said, practice final 1 seemed like a good place to start because when I looked at them, they're all kind of similar. Okay. So, practice final number 1. Okay. So what I want to do is just go through the long answers, and we are going to start at the beginning because that's the oldest, and so that's going to kind of need more review than the newer stuff, right? And so if we don't have time to finish all of these long answers because I yap a lot, then at least it won't be so bad, right? So we'll start at this really old stuff and work our way through. So the short answers, right, there's going to be 5 true, false, and then 15 multiple choice kind of short answer questions. I'm not going to go through those on this practice test because those are just there to give you an idea of what to expect. I don't want you to be kind of hooked on those exact questions, so that's why I'm not even going to bother. It's going to be a lot of theory from chapter 1 and chapter 2, mostly, right? There are other things in there, but mostly chapter 1, chapter 2, different variable types, different, how do we visualize this, that type of thing. So, but definitely go through. And I also found that the solutions that are posted, Jen's done a good job just kind of justifying why each of the questions or each of the solutions are what they are. But if you do have any questions, because obviously we all do solutions differently, and so if you're not understanding something in the question or in the solutions, then just let me know and I'll help you clarify. So like we talked about last day, the first long answer question is going to be a 5-number summary question. Find the outliers, draw a box plot. And so there's a couple of extra questions on here. They don't hurt, but I'll tell you right now that part A and B, you're not going to have to do on the final. We'll do them together just for review, but you're going to focus on C, D, and E for the final. Okay. So just things like that where it does some different stuff and different emphasis, but and you can do it. But we haven't really emphasized stem and leaf plots, for example. We went through them, but didn't really emphasize it. Okay. So we're given some data, and first part just says create a split stem and leaf plot of the height data. We definitely didn't spend that much time on stem and leaf plots, but one of the rules is that you have to have at least 5 stems. And so a split stem and leaf plot would just mean, okay, we have to split the stems. So there's a lower stem and an upper stem. So the lower stem gets the 0 to 4 leaves, and the upper stem, I get confused because it's physically lower, gets the 5 to 9 leaves. So I'll show you what I mean. Okay? Because if we look at these numbers, the first thing that we're going to do, especially knowing that we're going to make a 5-number summary eventually, is we're going to sort these data from smallest to largest. And so we're going to sort this data. And when I did this morning, I ran out of room pretty quickly. So I'm going to try to write small, but you'll have room on your page. But for me, 13 data points is a lot. So sorted, we have 58, 59, 60, and definitely on the final, if you're going through and sorting these, right, you'll want to cross them off as you go or something, just to show yourself that, oh, this one I've taken, and then just spend a lot of time making sure you have all the data points and all the right data points, because everything is going to hinge on that. So 61, I've got it Martha Stewarted here, so 65, 65, 66, 67, 72, I'm gonna run out of room again, 73, oh, fine, 74, 77, and 79. Ran out of room. So looking at these values, we've got 50, 60, and 70. Those would be our stems, right, for our stem and leaf plot. If we have to split these, what we're going to do is we're going to have a stem of 5 and then a stem of 5 star is what we usually do. 6 and 6 star, 7 and 7 star. So the plain numbers are going to get the leaves that are from 0 to 4, and then the starred numbers get the values, the leaves of 5 to 9. So we don't have any 5 stems with any of the lower leaves. So we have 8 and 9, right? 58, 59 on the 5 star. Like I said, this is not something that's on the final, so it's not something that I want you to worry about, but it is something that we did, so as well go through it. 60, 61 are on the lower stem of 6, and then on the upper stem of 6 we have 65, 65, 66, and 67. It's important that each number takes up the same amount of space, right? Because what we're doing is we're essentially making a histogram, right? So we're piling these numbers on top of each other, so they have to take up the same amount of space visually. Moving on to the 70s, so on the lower stem of the 7s, we've got 2, 3, and 4, 2, 3, 4, and then on the upper stem of 7, we've got 7 and 9. So here, if you tilt your head this way, I guess this way too, but easier this way. If you go and you kind of imagine this being a histogram, right? It's a 4-man's histogram. And so if we had to describe the shape of this, I'd say it's approximately normal. Okay. So you can draw a little. Part B. Describe the overall shape. If we had to describe this, right, the shape is approximately normal. in the solutions, I see they have unimodal, bell-shaped, roughly symmetric. I just go for approximately normal. They're all the same. We can throw in the center and the spread just to show off. Didn't ask for it, but may as well. Center, I'd say, is roughly around 65-ish, right? Just roughly around 65. And for the spread, well, we have the values. The spread is from 58 to 79. From 58 to 79. Good. Now for the part that actually matters, part C. Oops. Describe the data using a 5-number summary. So here's where we get to do our 5-number summary. Remember, a 5-number summary is the minimum, the Q1, the median, Q3, and then the maximum. So we've got the minimum, Q1, the median, Q3, and the maximum. They have to be in this order or decreasing, right? So maximum Q3, median Q1 to the minimum. I always start at the minimum and move to the maximum just because that's the way I read my numbers. Okay. But you can't have the quartiles and then the minimum and the maximum, right? Kind of hodgepodge. They have to be in order. So the minimum and the maximum, they're fine, right? We've sorted our data, 58 and 79. So let's throw those in. Kind of quick rewards here, 58, 79. Next, we're going to find our median. We use the boop, boop, boop method. Kind of tricky because I've got 2 levels, but here we go. Boop, 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 boop. So we've got a median of 66, right? So, and because you've landed on that number, you can't use it to find the quartiles, right? If you had taken the average of 2 numbers, right, that's when you circle it and draw a line down the middle, then the median is actually at that line. So you haven't used either of those numbers, so you could use them to find the quartiles. So definitely do a little bit of practice on those because it was a long time ago. So the median is 66. So now we can find our first quartile. So we can't use 66, so we start at 65 and 58, and we boop, boop, boop. And I land on 60 and 61, so I have to take the average of those 2. So my Q1 is 60 plus 61 divided by 2, which is 60.5. While we're at it, we can find Q3. Again, a little tricky because I'm on 2 levels, but we start at 67 and 79 and boop, boop, boop. I really some weird worm. And here, Q3 in the middle somewhere. Q3 is 73 plus 74 divided by 2, which is 73.5. So we've got 60.5 and 73.5. So there we have our 5-number summary. Great. Part D is where we have to find if there's any outliers, which you will have to do. To find outliers, right, we use the 1.5 IQR rule, which says that moving down from Q1, we can go as far as 1.5 times the interquartile range without having any outliers. Anything beyond that point, though, will be considered an outlier. Same thing, but up from Q3 right? That's going to be your upper bound. And so first thing we're going to do is we're going to find the interquartile range, which is Q3 minus Q1. 73.5 minus 60.5 is 13. So I'll first find the lower bound. That's your Q1 minus 1.5 times the interquartile range. So 60.5 minus 1.5 times 13. Feel like it was 19, but 1.5 times 13. Oh, 19.5. 60.5 minus 19.5. Oops. It's 41. We can have a quick look, right? But 41 is less than our minimum, and so there are no outliers on the lower end, right? Because all the data points are larger than the lower bound. So since the minimum value of 58 is larger than the lower bound, of 41, there are no outliers on the lower end. Now we'll find the upper bound. The upper bound, we're going up from Q3. So Q3 plus 1.5 times the interquartile range. Is it 73.5? Yeah. 73.5 plus 1.5 times 13. 73.5 plus 19.5, 93. And again, our maximum was 79, which is also inside this bound, so there are no outliers. Since the maximum value of 79 is less than the upper bound of 93, there are no outliers on the upper end. Therefore, no outliers. Woohoo! So now that we know that, in this next part, we're going to draw our box plot, and just a quick sketch is fine. And you do have to draw a box plot on the final. Display the 5-number summary in a box plot, adjusting the min-max whiskers if there are any outliers, right? And so what you're going to do is you're going to draw your upper and lower bound and extend the whiskers to there. And if there are any points beyond that, you have to indicate them with stars, right? Little asterisks. I don't know. I feel like it's asterisks. Although it should be asterisks. Anyways, really not important. But you do have to show outliers if you found any. Okay? And so I'm going to do just a horizontal line here. I'll start at 55, 60, 65, 70, 75, and 80. Because we were going from 58 to 79. So just rough sketch, right? You don't have to spend a lot of time on it. It's really just to see, okay, well, do you know how these bounds work if they're outliers or not? Okay. One thing that I will do that you don't necessarily have to do is that I'm going to do a little ... here. The lower bound was 41. Just to remind myself that the lines, the whiskers can go to this point, but not beyond there. Okay. And same thing, well, it's hard on here because this isn't actually at 93. I think it was 93. Yeah, but the upper bound is 93. So how do we draw a box plot? We're going to draw a line at the median, the quartiles, so Q1 and Q3, and then connect those to make the central box. And so our median was at 66. So I'll just kind of sketch it in here. Median is 66. Our first quartile was 60.5. So Q1 was 60.5. And then 73.5 for Q3, so somewhere around here. Oops. Of course, you're welcome to do a vertical one, right? I'm just doing a horizontal one for space reasons. But the ones we've done in the lab, they're all vertical, so if you prefer that, that's fine. And then our minimum was at 58. Draw it somewhere here. So your whisker. Oh, all these software updates. Okay. And then our maximum was 79, so I'll just draw a little. So these whiskers, right, are a little bit shorter than the box. I'm not going to dock marks or anything, but it's nice to see. Okay. So the maximum, 79. Nice. It was a long time ago, but not too bad. Any questions about that one? Then let's move on to question 2. So question 2, I noticed in the outline that I gave you the other day, question 2 was the tree diagram and question 3 was the binomial. But then when I had to look at the practice finals, question 2 is the binomial always and question 3 is the tree diagram. So what I'm going to do is I'm going to change the one on the final so it matches the order on the practice finals, just so they jive. Okay. But so question 2 will be the binomial. I don't know if you want to change the order that I gave you last day, but it'll match the practice finals. Okay. We'll just swap them. So question 2 is a binomial. So a particularly well-known restaurant chain and Canadian icon offers a chance to win prizes on every cup of coffee between February 6th, 2019 and April 17th, 2019. I wonder if those are the actual dates. I don't know. How much research went into making this question? According to contest details, the chances of winning a food prize are 1 in 6. In a random sample of 12 cups, what's the probability of having exactly 3 food prize winning cups? Okay, so this is where we use the binomial to calculate the probabilities, right, of exactly 3. And then in part B, now we do 12 coffee cups and we want to know what's the probability that you get 3 or fewer food prizes, right? So that's 3, 2, 1, or 0 prizes. And then part C, during the contest window, suppose you spend 66 days, so now blah, 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 you're buying 66 cups, and you want to know what's the probability of winning 17 or more food prizes. And so it says to use the normal approximation and to check the conditions. So this was a long time ago, right? But we have to make sure that we are expecting to see at least 10 successes and 10 failures, just like for probability questions, right? Or proportion questions, sorry. And then we can use the normal approximation and z-scores and the z-table to find the probabilities. So we'll start here. Oh, and these values, the 8 in the square brackets, that's just the number of marks that are available. Right? We do the same thing on our test, except I think I have a full square around mine. I don't know, can't remember. Oops. So first thing we want to do, right, is just make sure that the binomial actually makes sense. So to have a binomial distribution, we can only have 2 possible outcomes, which in this case, yeah, either you won or you didn't win, right? And so we'll call winning a success and not winning, obviously, a failure. So the probability of success, P is the probability of success and we're told that it's 1 in 6, so 1 over 6. So P is 0.166 repeating. I'm just going to use the fraction though, because you have to keep all those decimal places if you're using the decimal version, which is fine, but it's a little bit quicker to write just 1 over 6. While we're at it, Q is the probability of a failure. Which is 1 minus P, which is 1 minus 1 over 6, which is 5 over 6. Since we need it in our calculations, we may as well show it here. N is the number of trials, which in this case, we're saying, okay, in a random sample of 12 coffee cups, so we're trying to win 12 times, so N is 12. So these are just things that were given. So now we want to know what's the probability of having exactly 3 food prize winning cups. So what we want to find is the probability that X equals K, right, in general. So the formula, which is N choose K times P to the power of K times Q to the power of N minus K. Or I think on your, I have 1 minus P. Still. 1 minus P to the N minus K. But 1 minus P is Q. They're the same. So if we want the probability that X is 3, right, of exactly 3 successes, then we replace K with 3, which is 12 choose 3 times 1 over 6 to the power of 3 times, we already decided that 1 minus p was 5 over 6. So I'll just write that here, 5 over 6 to the power of 12 minus 3. 12 choose 3, 12, and then my NCR button is over the plus sign, right? So second plus, and then 3 equals, there's 220 ways that we could have exactly 3 successes if we had 12 trials. So I want you to think of the trials as the layers of your tree diagram, right? You'd have 12 layers of it, and you'd have to pick however many had exactly 3 successes. There's 220 branches like that, so you don't want to do that by hand anymore. So then 1 over 6 to the power of 3 is 0.00462963. Store that. And then 5 over 6 to the power of 9, 0.1938066699 times, recall 1 times 220, 0.197395,712. I'm going to store this because I already know that I'm going to need it for part B, where we want to know, okay, what's the probability of 3 or fewer, was it? Let's see here. Oh. That you get 3 or fewer, right? So that includes 3. So I know I'm going to need this probability later on, so I may as well store it. And there's a method to my madness here. I'm going to store it in 3. Because it's 3 successes. And because I did it this morning and I know what's coming. Huh? All right. I would probably just leave all these decimals. I wouldn't bother rounding because you have to keep all your decimals in your calculations. And so you're better off just leaving all of them. On the final, I'll say something like keep at least 4 decimal places or something like that. So, part B. So 3 or fewer, so we want the probability that x is less than or equal to 3. That's the probability that you have 0, 1, 2, or 3. Right? And so don't forget about that 0. Right? That's kind of a common mistake that I see, is that you forget the option of 0 winnings. So the probability that x is 0 plus the probability that x is 1 plus the probability that x is 2 plus the probability that x is 3. We've already found that last one, but we're going to have to go through and calculate 0, 1, and 2. So the probability that x is 0 is 12 choose 0 times 1 over 6 to the power of 0 times 5 over 6 to the power of 12 minus 0 is just 12. There's only one way that we can have 0 successes. We don't win, don't win, don't win, don't win, don't win, don't win. Right? We can't have a single win in there. So there's only one way that that can happen. And so 12 choose 0, you can check it. 12 choose 0 is just 1. anything to the power of 0 is 1. And so the one that we're interested in is 5 over 6 to the power of 12. 0.112156655, which is also the probability that x is 0. So the probability of winning nothing in 12 trials is 0.112156655. I'll store this in 0. 0 successes. Move on to probability that x equals 1. 12 choose 1 times 1 and 6 to the power of 1 times 5 over 6 to the power of 11. Notice that your powers just have to add to 12 always. 12 choose 1 is just 12. 0.166 repeating. And then 5 and 6 to the power of 11. 0.134587986 times 1 and 6 times 12. 0.269175971, which I will store in 1. Last one that we need to calculate, right, is the probability that x equals 2. So these are tedious, of course, but they're not hard once you figure out which probabilities you need. And then you just get to work. 12 choose 2. 1 over 6 to the power of 2. 5 over 6 to the power of 10. 12 choose 2. There's 66 ways of choosing 2. 1 and 6 squared. 0.0277 repeating. 5 and 6 to the power of 10. 0.161505583. Multiply those out, I get 0.296093569, which I will store in 2. So the probability that x is less than or equal to 3 is, I'm going to shorthand it even more. The probability of x equal to 0, we can just write p of 0 plus p of 1 plus p of 2 plus p of 3. Which is recall 0 plus recall 1 plus recall 2 plus recall 3. Make sure I didn't mess anything up. Okay, looks good. 0.874821907. And again, I would just leave all those decimal places. You worked hard to keep them, so why not show them off? And that's the probability that we're looking for. Yeah. Unless you find that there's, more than 3 or 4 zeros, right? So then you would want to go until you see some numbers, right? But if there's, I know it's hard to kind of talk, but if there's values in the first few decimal places, then you're safe, right? But if it's like 0.00003, then when you're adding those, you want to keep those. But yeah, should be safe. Okay. Cool. Let's do Well, any other questions about that one? Oh, let's do the normal approximation then, which is kind of the fun one, I think. So during the contest window, now you're traveling across Canada for 66 days. It's a lot of driving, I'm assuming. Maybe you're riding your bike. 66 days, yeah, maybe. Anyways, so you buy 1 cup of coffee each day from one of these well-known restaurant chains. Use the normal approximation. Make sure to test the conditions to find the probability of winning 17 or more food prizes during the trip across Canada. And so essentially what it's saying, I think the trip across Canada is supposed to make it a random sample of 66. I don't really know what they're getting at, but just fun to think about heading into summer. So we've got N is 66 now. And what we want is, we want to know what's the probability of 17 or more. We absolutely could do it by hand, just like we did in part B, right? But that would be 17 plus 18 plus 19 plus 20, all the way to 66. That sounds terrible. Even if you did the shortcut way and said, well, that must be the same as 1 minus 0 winnings, 1, 2, 3, all the way to 16, you'd still have to find 17 probabilities. So either way, it just feels really tedious. So what we can do is we can make sure that these conditions are met. And if they are, then we can just use the normal approximation. And so our conditions are the same as for proportions problems. We have to have at least NP greater than or equal to 10. And NQ has to be greater than or equal to 10. Right? We have to expect to see at least 10 successes and 10 failures is what that's saying. So in our case, NP is 66 times 1 over 6, which is 11, which is just squeaking by, but it is greater than 10. So it checks out. In our case, NQ is 66 times 5 over 6, which is 55, which is also greater than 10. So we can use the normal approximation. Conditions are met, so we can use the normal approximation. The normal approximation says that, okay, fine. So those conditions are met. Now you can use that mu is n times p, which in this case, we just saw was 11, right? So now we have a mean of 11. And sigma is the square root of NPQ, which in this case is the square root of 66 times 1 over 6 times 5 over 6. 1 over 6 times 5 over 6 times 66. Still under the square root, we have 9.166 repeating. Once we take the square root, we've got a sigma of 3.027650354, which I will round to 3 decimal places, let's say 3.028. Yeah. They will be. No, they will be met. So the conditions will be met. So that's not, yeah, if, yeah, if they weren't, you would have to do it by hand, but that's not something that I'm gonna make you do. But you still have to show that the conditions are met. That's the goal of the exercise. Yeah. Can you imagine? Oh, they're not met. Oh, shoot. It's going to take my whole 3 hours. I'd probably forfeit the marks. It's probably only 3 marks, so not worth it. So now we can use mu is 11 and sigma is 3.028. And so what we're looking for, right now that we've said these conditions are met, oh, kind of a skewed distribution, oh well. We can say, okay, well then it follows a normal distribution where the mu is 11 and sigma is 3.028. So now graphing what we're looking for in the question, right? We want to have 17 or more food prizes. And so 17 would be somewhere here. And we want to know what's the probability here. All right, so that's the area that we're looking for. We know mu and we know sigma. And so now we're back to kind of a basic Z-score problem where we have Z is X minus mu over sigma. For these binomial problems, it's just going to be X minus mu over sigma, right? So you're not going to have an N in there, even though it might feel like you do, but it got absorbed into finding the mean, right, NP. So now X is 17, that's the value we're interested in. Mu is 11 minus 3, or divided by 3.028. So we've got 17 minus 11, well, I guess I can check in, 6 over 3.028 is 1.981505.945. Z always has to get rounded to 2 decimal places, so we have Z of 1.98. Now we can use the Z table to find the area to the left. Remember, we always start with the area to the left, and if we need the area to the right, then we have to go a step further. So using the Z table, we find the area to the left, oops, of Z equal to 1.98 is, just cheating here, 0.9761. So I don't have my table out. But if someone could confirm, that would be great. So you're on the positive side for Z, 1.98. Good? Awesome. Thank you. So the area to the right is 1 minus 0.9761, which is 0.0239. So in 66 trials, the probability of 17 or more wins is 0.0239. Not that much, or not that high, I should say. Any questions about that one? After doing those proportions, hypothesis testing, and confidence intervals, and checking all those assumptions, now going back to checking the conditions for the binomial, kind of breezy, right? Done harder things. But you have to remember to check them. Okay. All right, no questions.
And it'll be set up like one you do by hand, and then the other one will be a normal approximation.
Yeah. Exactly. And it'll say, using the normal approximation, be sure to check the conditions. All right. So now question 3. is the tree diagram one. I'll just head back here so we can have a look at the whole question. But so you're running a daycare and have 5 infants and 8 toddlers. So suppose that 3 parents at random pick up their children. First thing we're going to do is just build a tree diagram, which is actually going to be a lot of work, right? Because we've got 3 parents picking up their kids, which means we have 3 layers. And then use the tree diagram to find some probabilities. So the probability that all 3 children are toddlers, at least 1 child is a toddler, at least 1 child is a toddler, given that there's at least 1 child who's an infant. Right? And so we can use the tree diagram to find all those probabilities. This one's a little bit trickier than what we've seen before, right? And that's kind of why I wanted to do this one. Because what we've got here is, okay, so we've got 13 kids in total, right? 5 and 8. And so, but after someone's been picked up, right? Now you've gone from 13 kids to 12 kids. And then another one's been picked up, so now you've gone from 12 kids to 11 kids, right? So the probabilities are going to be changing because depending on if the first parent picked up an infant or a toddler, right, that's going to reduce the number of either an infant or a toddler. And so our probabilities are going to depend on the previous branches. And so we've got 13 children total. So what I'm going to do is say, okay, well, sorry, I'm going to make this a little bit wider because I have to have 3 layers, each of which has 2 branches, right? So at the bottom, we're going to have 8 branches. So you kind of want to give yourself some room. And so we've got infants or toddlers. It's hard because I and T kind of end up looking the same. But this first layer is the first parent. The probability of them picking up an infant is 5 out of 13. And picking up a toddler is 8 out of 13. Next layer, we've got parent number 2. So now we've got the second parent, and there's only 12 children left. If the first parent picked up an infant, now there's only 4 infants left. And so here, same scenario, they can pick up an infant or a toddler, an infant or a toddler. So now there's 12 children left. 1 of the infants are gone, and so we've got 4 and 12 for that first branch. There's still 8 toddlers, so 8 and 12. Moving on to the next branch, the first parent picked up a toddler, so there's still 5 infants, so 5 and 12. And the first parent picked up a toddler, so now there's 7 and 12 toddlers. So far, so good. So now, each of these branches has 2 branches. 1, 2. So here, this is the third parent with 11 children left. They can pick up an infant or a toddler, an infant or a toddler, infant or a toddler, infant or a toddler. Oh. All right. First branch, another infant's been picked up. So now there's only 3 out of 11 infants, and all 8 toddlers are left. So 8 out of 11. One infant is gone for the next branch. So 4 out of 11. And one toddler is gone. So 7 out of 11. Next branch, one infant's gone, one toddler's gone. And so we've got 4 out of 11 and 7 out of 11. Notice that these 2 middle branches are going to be the same. Or not all of them, but a lot of them will be similar or have the same probabilities. For the last set of branches, right, we've picked up no infants, and so there's still 5 out of 11 infants. We've picked up 2 toddlers, so there's 6 out of 11 toddlers. Okay. I'm going to call this branch 1, branch 2, branch 3, 4, 5, 6, 7, and 8. So what I want to do is I want to calculate these probabilities running down each branch. So I'm going to have 1, 2, 3, 4, 5, 6, 7, and 8. If we write these out, branch number 1 is the probability of I. And I've Martha Stewarted these, but if you went through, so what you would do, right, is you would just multiply down each branch. So 5 over 13 times 4 over 12 times 3 over 11. And what you would get is 0.034965035. The second branch is going to be the probability of IIT, which I'll just give it to you is 0.09324000932. The probability of ITI is also 0.09324000932. For the probability of the ITT, my writing got a little messy here. Yeah, is 0.16317011632. Probability of TII is again 0.09324000932. The probability of TIT is again 0.16317011632. The probability of TTI is the same thing. So 0.163170162. And then the probability of TTT is 0.1958041958. Oof. A lot of work. Or a lot of writing at least. But now, what's the probability that all 3 children are toddlers? The probability of TTT is just 0.19580411958. So you can just steal that from all the work that you did in part A. C. What's the probability that at least one child is a toddler? So just looking at, well, you can look at the branches if you want. I actually think it's easier to look at these I's, whatever's. We want to know what's the probability that at least one child is a toddler. The only one where I don't have a single T, right, is this one, I. And so what I can do is, because I know that these have to add to 1, I can do 1 minus this one to find the probability that I want, right? Or if you wanted to go through and say, well, that's this one plus 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 this one, that's fine too. A lot more work, but it's fine by me. So the probability of at least 1T is 1 minus the probability of I, which is 1 minus 0.034965035, which is 0.96503496. Okay. For the last part, we want to know what's the probability that at least one child is a toddler, given that at least one child who is an infant, no, at least one child is an infant. Oh, there is, never mind, whatever. So what we're looking for is the probability that at least 1 T given, remember that straight up vertical bar is given that there's at least 1 I. In terms of probabilities, right, we can rewrite this conditional probability as the probability of at least 1 T and 1 I, dropping that at least 1 for the second one, over the probability of at least 1 I. The probability of A given B is the probability of A and B over the probability of B. The probability of at least 1 T and 1 I, if we look at our list, so we have to have at least 1 T and 1 I. So it's going to be easier to look at the one that doesn't satisfy or the ones that doesn't satisfy. This one doesn't have at least one t, so it's out, right? This one's good, this one's good, good, no good, right? So what I'm gonna do is I'm gonna do 1 minus this one and this one, because there's not at least one t and one I. So that's gonna be 1 minus the probability of I, and then minus the probability of t, over the probability of at least one infant, which is 1 minus the probability of a toddler. Which is going to be 1 minus 0.034965035 minus 0.1958041958 over 1 minus 0.1958041958. I do not have them stored. Okay, fine. 4965035 minus 0.1958041958. I get 0.769230077 over 1 minus 0.1958041958 over 0.804195805. We get 0.956521739. Whew. It's kind of the most outside the box tree diagram that was on the practice tests, but have a look at those other ones, right? Because it was a long time ago, and also we haven't really come back to work on that stuff. So I suspect it's going to need some more practice. But let's see here. Oh, let's get into the good stuff, shall we? Question 4. From what I remember, I'm pretty sure it's 3 up top and then 2, 2, 2. But what I'm going to try to do is make it make more sense. Because as it stands right now, it's a sports one. And for me personally, as soon as I see a sports reference one, I'm kind of like, I don't know how this works. And so, but what I'm going to have to do is I'm going to have to keep it as start with 3 and then 2, 2, 2. Right. So behind door number 1, you either win or lose, win or lose, win or lose. Right. Door number 2, door number 3, that type of thing. I'll see if I can put out a better practice one. But have a look at the other practice tests, right, first to see what's going on. Okay, so statisticians at, so question 4, statisticians at Wilmette. I don't know, we must be worried about like copyright, some sort of I don't know, we're very careful here. Statisticians at Wilmot have determined that the time spent by customers to pay for their goods has a mean value of 9.8 minutes and a standard deviation of 3.7 minutes nationwide. We will assume the distribution is normal. So here, this is one of those Z-score questions, right? So we've got a normal distribution with a mean of 9.8 and a standard deviation of 3.7. Part A, if an individual customer is selected at random, what's the probability that he or she will spend less than 5 minutes paying for his or her goods? Include a diagram. Just to read on. Part B, how long in minutes must a person wait in order to be in the lower 15th percentile of customers waiting to pay for their goods? And then part C, now you've got a sample size. So if 30 customers are selected at random, what's the probability that the average time spent by these 30 individuals will be between 5 and 10 minutes? Include a diagram. So kind of fun Z-score calculations. So our diagram here, we've got a normal distribution and we're centered on 9.8. At this point, I think most of you kind of prefer to draw the diagram because it helps you map out what you have to do in the question, right? And so you've got a normal distribution centered at 9.8 and sigma is 3.7. And what's the probability that they'll spend less than 5 minutes? So 5 minutes is somewhere here, and the area under the curve is a probability, right? So the probability that they spend 5 minutes or less, it's the lower tail that we're looking for. So now we can calculate Z is x minus mu over sigma. X is 5 minus 9.8 over 3.7. 5 minus 9.8 over 3.7. We get Z of negative 1.297297. Repeating. Z, we always have to round to 2 decimal places properly, right? And that would make it negative 1.30. So using the Z table, pull it out here. Wow. Using the Z table, we find the area to the left of Z equal to negative 1.30 is what? Negative 1.30 is 0.0968. You're welcome to write a little sentence, but it's not something that I'm going to be looking for. And because you want to keep your pace up, it's not something that I would even recommend doing. Here, you're done with this question. Moving on. Okay. So now, part B. This is one of those working backwards questions, right? So I give you the area under the curve and you have to find the X value that's associated with it. And so how long in minutes must a person wait in order to be in the lower 15th percentile of customers waiting to pay for their goods? So now, again, we've got this normal distribution centered on 9.8, and we want the lower 15th percentile. So at some unknown point here, this area, we're forcing to be 0.15, right? Remember, the 15th percentile is 15% below it and 85% above it. So now we know the area below it to the left has to be 0.15. So what we do is we look for the value closest to 0.15, and I'm between 0.1515 and 0.1492. You're just going to do a quick calculation. So 0.15 minus 0.1492 to see which one's closest. 0.1492 is actually closer to 0.15. So what I'm going to say is using the Z table, we find the table entry. So these values in the body of the table, we call them the table entries. The table entry closest to 0.15 is 0.1492, which corresponds to, right, because the whole goal was to backtrack now to find the Z that makes that happen, corresponds to Z equal to negative 1.04. So now we know Z is x minus mu over sigma. So negative 1.04 is x, which we're trying to solve for, minus 9.8, which is your mu, over 3.7, right? Sigma's 3.7, yeah. So negative 1.04 times 3.7 plus 9.8, I get x must be 5.952. And then you're done. And I'm out of time, so we'll keep going next day. See you guys on Wednesday. Oh, make sure you pick up your assignments here if you didn't get yours back. But I think just